Welcome, everyone. I am Dr. Kevin Woods, presenting the third article in my climate series titled Analytical Modeling of Atmospheric Solar Absorption. My expertise is in thermodynamics and heat transfer. The aim of this effort was to produce a method for determining solar absorption in the atmosphere using software such as Microsoft Excel. Sunlight is affected by two mechanisms in the atmosphere: absorption and scattering. The gases in the atmosphere absorb and scatter certain wavelengths of solar energy. Rayleigh scattering backscatters and forward scatters certain wavelengths and generates the blue sky. This graphic shows the absorption spectrum of the atmosphere and is readily available on the internet. Solar absorption is in the wavelength range from 100 nanometers to about 3 microns, shown in the red box. This is the focus of the modeling in this article. The absorbing substances in the atmosphere are shown with their relative influence on solar absorption and scattering. Water vapor is the main absorbing gas in the atmosphere and absorbs mainly in the infrared region of the spectrum. Carbon dioxide absorbs in the infrared as well, but overlaps with water vapor near the tail end of the Planck distribution, and so has a minimal effect on solar absorption. Ozone and oxygen absorb ionizing radiation where oxygen reacts to form ozone due to ultraviolet light, and vice versa. Hence, the ozone layer absorbs UV radiation. Methane and nitrogen oxides have negligible effects on solar absorption. Finally, Rayleigh scattering occurs in the ultraviolet and visible light regions of the spectrum, with blue light being most prominently scattered, leading to the blue sky. This article utilizes an analytical absorption model that was developed in a previous effort for atmospheric heat absorption, but is being applied for atmospheric solar absorption. From the journal article below, the absorption equation is given as shown. The only difference in the equation from the reference article is a change in B2 and C2 in the equation. This is due to the difference between solar radiation being directional and heat radiation being diffuse. B1, C1, B2, and C2 are all parameters in the equation for absorption. The parameters in the equations are described in the article but not the focus of this presentation. Of importance in this article is the angle theta, which is the angle of incidence of solar radiation from the normal. Sunlight impinges on the Earth at various angles, and the angle of incidence is shown here. Z is the altitude, while S is the path length of sunlight through the atmosphere. Using the analytical equation in Microsoft Excel and data from the HITRAN database, the solar absorption spectrum for sunlight with an incident angle of 0 is shown. The dashed line is the Planck distribution at the temperature of the sun of 5,780 Kelvin. The concentration of absorbing gases are shown as well, with the carbon dioxide concentration being 280 parts per million. Breaking the absorption down into each substance produces these three graphs for water vapor, carbon dioxide, and ozone. It is evident that water vapor is the most profound. The absorption spectrum produced in the model compares well with the absorption spectrum in the graphic. However, the spectrum varies with the angle of incidence and water vapor concentration in the atmosphere. The angle of incidence changes with time using the equations shown and depends on latitude, declination angle related to the day number or day of the year, and hour angle. Water vapor concentration varies in the atmosphere depending on surface temperature, which varies from 220 Kelvin to 320 Kelvin. These temperatures equate to water vapor concentrations from about 10 to 100,000 parts per million, and the absorption varies with angle of incidence. The profile converges on a dry atmosphere with a solar absorption of 5%. The solar constant is 1,365 watts per meter squared entering the atmosphere. This solar constant is on the cross-sectional area of the Earth, but the Earth's surface area is 4 times the cross-sectional area. The angle of incidence not only affects the path length traversed and solar absorption with time, but also the total energy impinging on the surface with time. For a specific location on Earth's surface, the average annual atmospheric solar absorption is calculated using these two parameters. Averaging produces the following graph of atmospheric solar absorption versus latitude. Assuming an average annual temperature range from 260 to 300 Kelvin, you can see the variation with temperature. Using annual temperature data from the Climate Research Unit in the UK, the annually average atmospheric solar absorption for each latitude is approximated by the following equation. The simple equation is fine for modeling Earth today, but a more robust model determines the solar absorption based on the surface temperature and latitude. This equation may be utilized to approximate long-term climate variations such as ice ages. In summary, the main component of atmospheric solar absorption is water vapor. Carbon dioxide, methane, and nitrogen oxides have minimal influence. The analytical model is accurate compared to reference data, as was shown with the graphic. The outputs are a robust atmospheric solar absorption model and a simple model based on latitude. My future work focuses on modeling more parameters relating to Earth's climate to integrate into a previously published climate model for the Earth. The goal is to provide credible evidence validating or invalidating climate claims. I'd like to acknowledge the HyTran website for the absorption line data utilized in the model. The database is available at hytran.org. For the entire article, please go to prosejournals.com. Thank you, and please subscribe and click the bell for notifications.